and we're going to hear about creativity. We have another renowned scientist, a former Bell Labs researcher, Bob Marcus, who's been doing a lot of work at Bell Labs and then had a second career where he came to NJIT as a research scientist. In between, he worked at Bellcore as part of the split up of the Bell system, and then he moved into an art career, and he's going to talk to us about creativity. And for those of you who would like to see some of his work, if you go over to Eberhard Hall and you stand on the first floor and you look up the stairs, you're going to see a phenomenal sculpture, a Klein bottle that Bob created and was donated and dedicated today to NJIT. Before we let Bob get up, though, I'd like to introduce one of his colleagues who had worked with him here at NJIT, Roy Cornelli, who'd like to say just a few words. And I'm sure you're going to find the second half of the presentation as enthralling as the first half. Roy?
I was asked to share with you some of the observations about Bob, and I worked with him for 2 years. Actually, it was at Bellcore when we tried to start up a seamless connection between the university and industry. As mentioned, Bellcore collapsed in '91, but this was during the '90-91 period. Bob was outstanding, world-known sculptor, which involves art and science together. He was also an excellent manager, writer, and speaker. He was highly organized and very creative. In the evenings, Bob would make sculpture on the meter scale. He had a 2100-degree furnace in his backyard just on the border of falling down a steep slope. He had a couple of them. And the key was to melt this bronze and pour it into molds, and involved a combination of technology and other things. On the nanoscale at Bellcore, or the atomic scale, he made the world's sharpest needle. It was a needle like this, and with the transmission electron microscope, you could see the tip of the needle was a single atom, and that was quite a breakthrough. Also, with his expertise in diagnostics, scanning electron microscope, we also looked on atomic phenomena on the wall of a silicon slab, for instance, and you could see that the ridges and so forth in the scale on the wall. On the micron size, on the micron level, we worked on a joint project to make a diving board that was 300 microns by 5 microns, and it was movable, and it had a vertical mirror on the end. Again, this involved a lot of creativity. To get the smooth wall, we had to etch down vertically and not into the wall, and there's a selective etch with a very dangerous chemical, EDP. I was doing that with a mask on, and in order, when you etch, it removes material away, but the key is that you got to keep getting fresh etching on the surface in order to get the etch rate going down to be 1,000 times more than the etch rate going in, which is not supposed to etch that particular plane of silicon. So it involved making this special design only Bob could think of a pulsating, the sample was mounted in a pulsating rod going like this and rotating this way, and at very high speed of RPMs that removed the etching, and it was quite a piece of work. Okay, and so those 3 areas Bob worked on. He's also known at Bellcore and Bell Labs as an expert in diagnostics of semiconductors. Basically, you can look at this field as shooting electrons, photons, ions at a surface of a sample and looking at the atoms and the scattering off the front surface and the transmission. So there's about 30 different technologies, and Bob wrote a chapter on the BLSI technology book that was edited by Simon Z. I think I should leave and get Bob up here as quickly as possible. But in closing, just let me say, though trained as a chemical engineer, he used fundamental ideas, mechanical, chemical, and electrical, and merged these together with his creative powers. Bob?
Thank you very much, Roy, for the kind words. This is the wrong, how do I do?
Your reflections on creativity, right?
Yeah. Okay, here we go. Thank you. Just to pick up one thought from the previous speaker, it used to be the case that universities like to have departments of mathematics because they were very inexpensive to operate. All the mathematicians needed was a pencil, a paper, and a wastebasket. Then the economists came along and they were even cheaper because they don't use wastebaskets. Okay, the title of my talk is Reflections on Creativity Based on My Art and My Science. And this was given to me as an assignment by Jay Caprath. And it was an interesting assignment. I enjoyed working on it. I'd like to divide my talk into three parts, not too formally, but the three parts. The first part, I'd like to make some general observations and comments and analysis of creativity. What do we mean by creativity? Where does it come from? What is it? How does it fit into the human condition, the mind, the human soul, whatever? What is creativity? And then the second and third parts, I'd like to talk about creativity as I think it's been exemplified in my science and in my art. Okay, let me start by saying, with all due respect to Descartes, I'd like to make a slight correction. How do you advance these things? Where's the advancement? I don't know how to work this.
This thing either.
Does this thing work?
This should still work. Use the
Okay, thank
button
you.
will advance you. You raise a pointer right on there, and that brings you back.
Uh-huh.
So click the right arrow button to advance.
Very good, thank you. Okay, now I know how to work this. With all due respect to Descartes, I really do think he had it backwards. The famous saying is, I think, therefore I am. To my way of thinking, actually, what comes first is the I am. That is what's profound, to think that, to know that I exist, that I have a consciousness, I'm self-conscious, that there is an I, an ego. I am that I am, to quote some other source. This is quite something, I am. And from knowing that I am comes, therefore I think, I eat, I create, I sometimes feel spiritual, I get angry, and so forth and so on. And as I said, I create. So the I am, I think, comes first. And creativity is one of the things that I do, just like I think, and I sleep, and I do many other things. Let's go to creativity and go to a definition of creativity. And to get a good definition of creativity, I went to that modern version of the Oxford English Dictionary, affectionately known as Wikipedia. Wikipedia has a very concise, very short, and rather practical definition. It's not perfect, but it works. They say that creativity refers to the phenomenon whereby a person creates something new that has some kind of value. Now, I know there's some tautology here. Creativity is when you create. It's a little kind of strange way of putting it, but I think you get the idea. And it has some kind of value. Who puts the value on it? It could be the person doing the creation. It could be an audience or whatever. But it's not making something that has blah interest. It's something that is of interest somewhere to somebody. It's got some kind of value. And we can think of, obviously, many ideas of creativity. Practical, the invention of the electric light bulb. But we don't have to stick with things. We can go into government and politics. Grover Nordquist's plan to starve the government and thereby make it shrink. It's a creative ideology, isn't it? You may not like it, but it's a creative thing. Many people, when they think of creativity, of course, think of art. Picasso's Guernica is a creative act, certainly. It speaks to our aesthetic value. It also speaks to our social values. The Guernica was made as partly as a social protest against the Civil War in Spain. There's creativity in music, there's creativity in dance. A very popular dance group today, modern dance, is Pilobolus, very, very creative people. You can do something seemingly trivial, like create a shopping list for the weekend. It's trivial compared to some other grand things, but it is a creative act. If you want to tell a story to your child, to your daughter, in such a way that it puts your daughter to sleep, that's also a creative act. Now, this guy wasn't succeeding too well, but there are lots of ways of being creative other than just the usual ones, if you pardon my saying so, in science and in art. Interestingly enough, I think that there's so much enjoyment out of creating something, making something. Well, sometimes it's trivial, but sometimes it's grand. There's a lot of enjoyment. And yet, as far as I know, the idea of exploiting our creativity is not a part of any of the Western religions of the world, to my knowledge. None of them suggested that's something that we ought to do, but I think it is something we ought to do. Okay, let's look at some of the social consequences and emotional consequences of creativity. What impact does it have on the rest of us? We can, first of all, creativity, depending on what field it's in, it speaks to qualitatively very different kinds of things. We can talk about the aesthetic appeal of a creative act. On one extreme, it has no aesthetic appeal whatsoever, or it can have high aesthetic appeal, or it could be someplace on the continuum. Forget about aesthetics. Just talk about it, whether it's a big thing or a little thing. It could be something grand, the theory of relativity, if you will. Trivial, the shopping list for tomorrow. These are qualitatively different features to look at, and for each one there's a continuum. It could be something very practical, the electric light bulb, or speak to the soul is my idea of the opposite extreme. There can be in the political arena, we can think of creative political ideologies that many of us would consider good, as exemplified by Martin Luther King or Mahatma Gandhi, for example. And we can think of people who've made ideologies on the other extreme. So there are a lot of social and emotional consequences, and they run the gamut from each one to run the gamut from one extreme to the other. All right? What do we need to be creative? There's a lot of talk about right half of the brain, left half of the brain. I think that there's a lot more that may have been somewhat of an oversimplification, but let's look and see what we think we need to be creative, assuming we want to be creative. For all acts of creativity, we do need imagination. If you don't have any imagination, you're screwed from the beginning. You won't get anywhere. You got to have some imagination. And you probably can't learn it. For some acts of creativity, you need special knowledge. So for some, you don't. But for many, you do. Sometimes, like the previous speaker exemplified very clearly, for some acts of creation in science and other areas, you need, in addition to specialized knowledge, you have to be able to reason and think clearly and well. For some acts of creativity, thinking clearly is not the requirement, but maybe you need some technique. For example, if you want to draw a picture of something, abstract or not, how do you apply the paint to the canvas? It's a technique. You can learn it. You can learn technique Maybe you can't learn this. You can, if you're missing knowledge, you can learn the knowledge. You can just go to school or whatever. Imagination you probably can't learn. There are blocks to creativity that stop it. Certainly if you're missing something, essential, that will stop you from the quick. If you have no imagination, as I said, forget it. If you need knowledge, you're missing it, you can't do anything, but you can learn the missing knowledge. Intelligence, technique, you can learn technique and so forth and so on. Missing something is something that really stops one from being creative in a certain area that you want to be creative. Fear of failure, that's a biggie. That's a big one. Many times, I don't know how many times I've talked to people about sculpture or whatever, and they say, oh, I can't do that. Well, how do you know you can't? Oh, I can't. Have you ever tried? No, but I know I won't be able to. I can't. I'll fail. Many people are afraid of failure, and they don't even give themselves a chance. Interestingly enough, I think that this fear of failure also has a cultural tie-in. There are some cultures on this earth where people are, the prevailing opinion is that if you try something and fail at it, you're ashamed. It's a shame to fail. If you take a risk and it doesn't work out, it's shameful. And of course, the consequence is you don't start in the first place. Other cultures, this is not such a shame. And so some cultures, I think, are more nicer than others regarding fear of failure. You can be taught to avoid creativity. When I was in grade school, first, second, and third grade, nobody told me this, but I could sense it from my environment. Boys didn't do art. Girls did art. That was the prevailing opinion when I was a little kid. I think a lot of that's gone today, but thank God. And finally, you can be very creative and very potentially able to do great stuff in whatever field. But if you're lazy, forget it. If you're a couch potato and you prefer to watch television than something else that you could do if you wanted to, that sort of nips it in the bud, doesn't it? So inertia or laziness is a big impediment, which again is different for different people, certainly. Now let me go to my own approach in science and art. I want to say just a couple of things about myself. I'm going to open up a little bit to you. That's what I was asked to do. Where is he? I don't know where he is. There you are, Jay. By Jay. One of the things I like to do, well, I like to use my imagination. Most of us do. I like to use my hands. I always have. When I was a kid, I loved to make things and build things with my hands. And I still remember an incident when I was starting out at the University of Chicago, where I was an undergraduate student. During my first year, I wanted to get a part-time job in a physics lab. And I know there was an opening under Professor Lothar Meyer. Lothar Meyer at that time was a low-temperature physicist, and he had a laboratory inside the West Stands of Stagg Field. The West Stands is where the first nuclear reactor was built and successfully tested in 1942, I think. Anyway, at the end of the Second World War, there are still many research physics labs there, and they remained there in the West Stands for about another 10 or 15 years until they were dismantled. But Professor Meyer had a laboratory there. So I went to see him to apply for the job. And I started telling him how great I was, how I used to make a radio set and this, that, and the other. And I remember him saying, he waved his hand, he said, "Stop, I don't want to know any of this stuff. So what I want to know is, do you have common sense and can you work with your hands?" Well, I was astounded. I mean, I didn't really appreciate common sense when I was 17 years old. Subsequently, of course, I learned how important it is and how rare it is. But I really was impressed when he said, "Can you work with your hands?" Because I like to work with my hands. I like to make things. And nobody ever told me it was a great thing to do that. But here was this professor at the University of Chicago, a physicist, for whom working with your hands was clearly a very important thing. And it was a stamp of approval on something I like to do. So I really enjoyed that little comment by him. Also, since I was a kid, I suppose, I, like many of us, found out what I liked to do and tried to do it. Most of us did in some way or another. This was codified many years later, about 10 years ago, by Joseph Campbell, who some of you may remember. He was sort of a popular psychologist, philosopher, I don't know, and he had a TV program for a little while. But one of his adages was to follow your bliss. That is, look into yourself and see what it is you like to do and do it. Don't just wait, do it. So long as it's not illegal and it doesn't do anybody any harm, of course. But if it meets those two requirements, and if you find that you like to do something, for heaven's sakes, do it. Why do you want to hold yourself back? Exploit your basic needs and instincts. And that's what Campbell said. And of course, that resonated very, very nicely with me. All right, creating visual shapes. What did I do here? Nuts. Let me go back. I don't know what's going on. Help. I think I got out of PowerPoint. Creating the visual shapes with some aesthetic appeal. Well, while he's doing that, let me read this. Creating visual shapes with some kind of aesthetic appeal has always been important in my art. I know that. I could talk about aesthetics in my art. But then I was asking myself, what about science? I mean, Jay Capraft gave me the assignment to talk about creativity in my art and my science. Now, the usual kind of creative goals in science are the ones that were clearly exemplified by our previous speaker. You want to push back the frontiers of science, understand nature better in some way. I knew all that. But what I was asking myself was there some kind of artistically directed creativity also going on in my work in science? Is there something similar to my work in art that was happening in my work in science? I was curious. And I went into that, looked at this question in preparation for this talk, and I quickly found that the answer was yes. It surprised me, but it was there. And in my scientific career, I did a lot of microfabrication and a lot of visual studies of interesting, nice, cute kind of structures, usually very, very small. Very often I had to look at those things with electron microscopes and various other microscope tools. I got involved in making nano devices along with Bill Carr. At that time it was called micro fabrication or something, I don't remember. MEMS. But it morphed into nano devices. I enjoyed making a lot of these microstructures, and I enjoyed throughout my whole career. And even though sometimes these little devices and structures that I made were kind of ancillary to the main research. Let me give you an example. Now, I want to show you, well, first let me go to this next slide.
Go to that slide.
Okay.
That's
I don't want to start
you can't go to that slide. It will lock up PowerPoint right now.
No, that's a still slide. The next one was the video.
No,
okay. One of the things that I did here with a student right here at NJIT about 1997, 96, the student was a Ph.D. student working on some MEMS or nanotechnology project. And one of the things he did is make a bunch of cantilevers. Yeah, not yet. I don't want to start the movie just yet. Made a bunch of cantilevers, and here's 1, 2, 3, 4, 5 of them. This is 100 microns long, so the cantilever is 200 or 300 microns long. They're about 30 microns wide and about a micron or so thick. Each cantilever is made of 2 different materials with 2 different coefficients of thermal expansion. And on top of each cantilever was a thin wire that came out to the tip and came back. So it was possible to put a little electric current through a wire and heat it up. And when the cantilever heated up, since these 2 materials had different thermal expansion characteristics, it would bend in one direction or the other. We thought it would be fun to look at this inside the scanning electron microscope and see what it looks like when we pulse 1 cycle per second, 10 cycles per second, and so on. And then what about when we hit the resonant frequency? We calculated that the resonance frequency of one of these cantilevers is about 8.2 kilohertz. It's 8,200 times a second. If we pulse it at that frequency, we would hit the resonance frequency, and let's see what happens. Now I'm going to show the movie, I hope.
Yes, no problem.
Oh, I see. Good, thank you. Thanks. Okay, this is 1 hertz, 1 cycle per second, and now it's 10 cycles per second. The excursion is about 15, 20 microns from top to bottom. It's about 50 microns. If we go to 100 hertz, it can't follow the impulse. There's a thermal lag, so it's a little bit less excursion. Now we're locating the resonance frequency at 8.16 kilohertz. Look at that. Look at the excursion. It's fantastic. This is really a vivid demonstration of what happens when you take a structural member like that and you hit it at the resonance frequency. It really vibrates, much more so than just a simple 1 time a second or 2 times a second. The next one, good.
Next video?
Yeah, but don't start the movie. I just want to talk about it first. Thank you. That's fine. Great. Okay. Another student, this is about the same time, was working on a different project, and this one was quite ancillary to his main thesis, but it was kind of interesting anyway. This is inside of a scanning electron microscope. This is, again, 100 microns. This is a gold wire. The diameter, it's about the size of a human hair. The diameter of this gold wire is about the same size as the hair on your hair in your head. Those of us who have hair in our head. And at the end of the gold, we had melted the tip, so it became rounded. So this is a gold wire, and here's one of those cantilevers bent down. Now, I call this the smallest functioning musical instrument in the whole bloody world. It not only is a musical instrument that looks like one, but it also makes a sound, and I'm going to show you in a second. View this, if you will, as an anvil, and this is the hammer. Okay, now start the movie. It's only about 10 seconds with sound. Isn't that fantastic? Il Trovatore. Okay, the rest I can handle because the rest are just slides. Notice the deep bass resonance coming from this micron-sized instrument. Okay, that's fine. Thank you. Not all of the structures and cute devices and shapes that I made were irrelevant to science. Some of them were turned out to be quite relevant. I'm only showing you a few here. Roy Corneli alluded to this one. Back in 1989 at Bell Labs and then Bellcore, I was doing some work on looking at the effect of controlling the oxidation kinetics of silicon surfaces to change the shape of a surface. This is not a flat silicon surface. This is a surface with some kind of a corner shape to it. And what we made was, at that time, we thought it was probably the world's sharpest needle. This is silicon, and these little black and white spots, they're not atoms, but they represent the sites of atoms. This is an amorphous layer covering it because of the poor vacuum inside the transmission electron microscope. But at the tip of the needle, you just see a few atoms at the tip. This had quite interesting and important relevance at the time. It seemed as if it did, in 2 different areas. One was the atomic force microscope, or the scanning tunneling microscope, was rather new at that time. And people were very much interested in looking to see how to make very, very sharp needles to use in the atomic force microscope. And this was an ideal shape of a needle. And also at that time, there was a lot of interest in a subject, the field called vacuum microelectronics, which seemed to be very important then in two areas. One was that it was thought that if we can field emit electrons from here, a ton of electrons off the surface of the tip to an anode, so this is a cathode, there's an anode here, a few tens of microns away, we essentially go back to the vacuum tube and replace the transistor, but the transit time for electrons through free space was faster than the transit time through semiconductors. So this seemed to offer the promise of very high-speed triodes or transistors types things. And the other application of this at that time seemed to be flat panel displays. That is, this by having millions of these little needles on a surface, each one emitting electrons, and having a phosphorus screen some few tens of microns away, you can have a flat panel display, basically with millions of little CRTs. And there was a company that commercialized this and actually built an some operating CRTs operating in color. The company was called Leti, a French company. But the technology actually didn't go very far beyond that, and for reasons which I don't understand. Okay, in summary, the experimental science that I've been involved in my scientific career generated some amusing and attractive mini sculptures, which sometimes did have scientific or technological value by themselves, but sometimes not so much, but it still were fun to make and fun to observe, and I got a big kick out of it, and I think my students probably did too, at least I hope they did. Now, the shapes and structures of these micro devices, or what you want to call them, of course, they're governed by the properties of the materials and by the nature of the experiments necessary for advancement of science, sometimes more so and sometimes less so. But if you really want to make some things which are aesthetically pleasing in 3 dimensions, for heaven's sake, go directly to art. Why go through science? So I did that, and I just want to make a correction. I didn't start my sculpture recently. I started about 35, 40 years ago. So actually I was wearing 2 hats at the same time, science and sculpture, for a long time. And I think it's somebody, Roy Conini mentioned, I also had a foundry, which I used for casting my bronzes. I'm getting ahead of myself. In sculpture, I rather soon learned that what was most satisfying to me was to cast sculpture in bronze. I like the idea of casting because for me, it gave me the biggest amount of freedom to design whatever I wanted to design based on aesthetics alone, not restricted at all by the original shape of the material, whatever it is. So I was never much interested in constructive sculpture, but rather in cast sculptures. Gave me a lot of freedom, which for me is important, somebody else it's not. And I turned to bronze because bronze is quite strong, and you don't have to pay too much attention to the fragility of the material. You have to pay some attention to it, but not too much. So you can basically design whatever you want, aesthetically pleasing curves, small regions, and you can realize in the bronze, and that really appealed to me. So most of my work is done in bronze by the lost wax method. Now, what is a lost wax method? This is a very busy slide. I'm only going to show you 3 pictures on here. Don't worry. The lost wax casting of bronze sculpture. Let's say we start with a piece of sculpture, looks like a vase. Maybe it's made of clay, soft clay. Maybe it's made of glass, wood, doesn't matter. I want to make this into bronze. Here it is in bronze. It's hollow. All bronze sculpture above a certain size, they're always hollow. Though the small bronzes are solid, but it's hollow. I want to go from here to here. How do you do it? Well, the first thing I have to do is make a mold of this and make a wax casting. So here's a wax casting of this. This is identical to that. The wax wall is only 3/16 of an inch thick. Now I take that wax casting and put it inside of a refractory material, ceramic or some investment material. So here's the wax sculpture inside here. And this yellow is some refractory, something that can withstand 2100 degrees, 2200 degrees Fahrenheit. I also have some extra wax pieces here. This is so you can pour in the bronze and this is for the gases to escape. But the sculpture's in there. There's no air anywhere in here, but there will be. This is heated up to a temperature to remove all the wax. So instead of having wax, we got space, hollow in here. And this gives rise to the term lost wax. That's where the idea of lost wax comes from. So now I have a mold with the sculpture in negative space. Melt some metal and pour it in here and fill it up with metal. This metal can be bronze, steel, aluminum, lead. In my case, it's always bronze. Then the last thing is to remove the investment, chip it away, make some repairs, and you end up with a final casting. So that's basically the technique. And I had my own little foundry, which I used for about 35 years for casting my own pieces, except when I had a commission, then I turned that over to a professional foundry. I never paid any, I never used my own time to make a piece that somebody else wanted. But for my own exploratory work, I did. Let me give you some examples of, just a couple of examples of the type of work that I do, that I have been doing. This is life size. It's a bronze figure, and it's not a typical nude. That is, if you look carefully, you see a lot of empty space. It's not solid bronze. It's got a lot of missing parts to it. And again, this is life size. Another one is similar to that, is this one is two people in an embrace. Again, they're missing parts here. It's and the viewer has to fill it in with your own imagination. These are the kind of things I like to do. As far as my bliss or whatever, I like to, I've had a lot of fun with topology, simple topology, topological ideas, and also the use of negative space. I'd like to illustrate that now. Let's start with some topology, some topological ideas. Most everybody here probably is familiar with the Möbius band. It's a band with the one side, one surface. You follow this all the way around, you come inside, follow it around, you come outside again. This is a Möbius band, and this is a curved two-dimensional surface. Here's Escher's rendition of a Möbius band with some large ants crawling all over it. I was thinking of this one day, I thought, wouldn't it be fun to do this in 3 dimensions? If you look at this as a section of a donut or a torus, and you see that the cross-section is triangular cross-section with each of the 3 sides are slightly convex. And if this triangle, if you move along this donut, rotate this triangle counterclockwise. And if you imagine this end coming around and connecting to the first end again, so you connect the blue to the blue to the red to the red, you do have a 3-sided surface. You have a blue side, red side, and the hidden side, yellow or whatever. And any 2 colors, any 2 surfaces are separated by an edge. However, if you come around and connect this here, but give it a 120 or 240 degree twist before connecting it, you end up with a one-sided surface. That is, if you start with blue, go all the way around, you find yourself on the red side, go all the way around the yellow side. So it's like, in a way, like a 3-dimensional analog of a Möbius band. So I thought it'd be fun to make that in bronze. I never saw it, never heard of one before, and I did. I made a few of them. This is one. This is an indoor sculpture called Continuum. You could see an edge right here. Here's another edge. But again, this is a one-sided surface in the sense in which I just described it. It's not a 3-sided surface. It's a one-sided surface. Another bit of fun I had with topology, and actually one of the reasons I guess I'm here today, is the Klein bottle was an invention of mathematician Felix Klein a century ago, and it's a realization of a one-sided bottle. This is a bottle, it's a vessel. You can pour something in, you can pour in water or beer or whatever, and it'll fill it up to about this level here. There's a hole in this wall. So the liquid will start coming out of the hole, but up to that hole you can fill it up. So it's a vessel. It's a glass or a bottle. It's a bottle. But it has one surface. I'm not going to take time out now, but if you put your finger on surface and go around. You end up inside, you come on the outside again. And this is the one that I thought, I thought it'd be fun to see this in 3 dimensions. I've seen a number of these things made of glass. Back when I was a graduate student, I remember the glass shop used to make these Klein bottles in the summertime for mathematics teachers that were there to take summer classes. And they loved to take these Klein bottles back to their students. But those were in glass. And I thought it would be kind of nice to see this in bronze. So I did. And this is bronze that I donated here to NJIT, and it's in Eberhard Hall on display. I'm not going to go through it now, but if you can go and take a look at it, and you try to trace your finger around, you'll see that it has one surface. This doesn't look like the Klein bottle that I showed in the previous picture, but topologically it's the same. And I call it, petit bouteille. This is my joke. Klein bottle. Klein was the name of the mathematician Felix Klein. In German, Klein means small, little. So this is a little bottle, just a modest attempt at humor. I also like to work with negative space, but in a positive way. That is, make negative space as important as positive space. What do I mean by that? Look at this one. This is we call it a profile cup or a loving cup. This is the same cup under 2 different lighting conditions, the same orientation and same cup. With this lighting condition, you can see much more clearly a profile here and a profile here. There are 2 faces. There's a woman's face and a man's face. This man had a mustache. But there are 2 faces. When you have it lit in an ordinary way, it may be hard to see the 2 faces. Generally, once people see the 2 profiles, it's easy to see again. When people first look at this profile cup or loving cup or vase, many people sense it's not right. It's something awkward about it. They sense it's not symmetrical, but it's hard for most people to figure out why. Well, of course, the reason is that you have 2 different profiles here, and the connecting lines necessarily, of course, are not symmetrical. You go from one profile to the other. Again, I think most of us have seen this kind of a thing in print with one profile on both sides, and the question is, what is it, a vase or a profile? Some articles on psychology or mathematical puzzles. But I've never heard of this in 3 dimensions, and at the same time as I thought of making this in bronze, I was thinking, why not have 2 different faces? Why have 1 face? Let's try 2 faces. So this is a profile cup with 2 faces. But again, the negative space here is very important in recognizing what this really is. And finally, the last one I want to show you is it's a wall relief, again in bronze. It's quite heavy. This is about 3.5 feet by 3 feet. And you can see the 2 figures. This is the back side of one and the front side of the other. This neutral plane, the back surface, is kind of undulating. It's not flat. It's sort of an undulating surface. And this back figure is in bas relief. It sticks out toward you from the screen. It's the way we usually see reliefs. The negative figure, however, is done in negative space. That is, the frontal view of a figure, but all of the features are dug down below the surface. It's in negative space. And the positive figure and the negative figure, meet right here with the fingertips, kind of analogous to Michelangelo's picture on the Sistine Chapel of God handing life to man. No blasphemy intended, but there is a vague similarity to that. This is all I want to say, I guess. In fact, this is my last slide, but again, I want to illustrate how I use negative space in a very major, important way, not just missing material, but it actually makes the shape. In summary, I'd like to summarize by saying my own creative instincts have been in art to play with shapes and things with visual impact. I just like to make things and things that are nice and fun to look at and have some aesthetic appeal. And in art, I particularly like to have fun with negative and positive space also with just simple topological ideas, one of which is the Klein bottle next door. And the last thing I'd like to say is I really wish that more of us would give ourselves the chance to explore our intrinsic creativity and to exploit, not just examine it, but exploit whatever intrinsic need we have to create and to make things. Follow your creative bliss. It's fun, it gives a lot of satisfaction, and if more people would spend more time doing this and less time arguing politics and fighting wars, it would be a much better world that we live in. Thank you very much.